Okay, we're ready for part 2 of section 6. This is the third method that I'm going to show you how to solve polynomial equations. This method is called the rational root theorem. You should have seen this method in Algebra 2. The rational root theorem is a pretty cool method because if there's a rational zero, we can know where they come from, or at least we can narrow down the pool. So in this particular equation, I've just said solve it. Now, grouping doesn't work. Factoring doesn't work. There are no other special formulas to get this one to work. So you have to basically just start picking roots and guessing them. Well, there's a lot of roots to pick from when you consider the idea that there's an infinite amount of numbers. So can we narrow this down? Well, it turns out we can. Look at the leading coefficient 2. The factors of 2 are plus and minus 1 and plus and minus 2. Now look at the constant term. 4. The factors of 4 are 1, 2, and 4. What you've just done is narrowed down the pool of possible rational roots to the following. And we call these the P over Q's, and I'll explain more about that later. Basically, take every single factor of the constant and divide it by the factors of the leading coefficient. So 1 over 1 is 1. 2 over 1 is 2. 4 over 1 is 4. So now you've divided everything by 1. Now divide everything by 2. So 1 over 2 is 1/2. 2 over 2 is 1, but we've already used that. And 4 over 2 is 2, but we've already used that. So these 8 numbers, 4 positive and 4 negative, are the possible rational zeros. The possible rational zeros. Well, what you do is you just pick one. Start with the first one. Start with positive 1. And put it in the hoopty. In the hoopty. Your coefficients are 2, negative 9, 3, and 4. And you just depress this polynomial and see if you can show that 1 is a root. So drop your 2. 1 times 2 is 2. Negative 9 and 2 make negative 7. 1 and negative 7 is negative 7. 3 and negative 7 is negative 4. 1 and negative 4 is negative 4. And that's 0. Ding, ding, ding. Check it out. You are good guessers. X equal 1 is a root. And the even cooler part is you've depressed this down to a quadratic. And hopefully now this bad boy will what? That's right. You said it. Hopefully he'll factor. And he does. He factors to 2x plus 1 and x minus 4. So x could be negative 1/2. X could be positive 4. And also, don't forget about this guy over here on the left-hand side of the screen. X could be 1. We got 3 rational roots. 3 real rational roots. That's how the rational root theorem works. So there's some guessing involved, and it can be a little tedious, but at least you've narrowed down the pool of infinite numbers. One way to cheat is to graph it on your calculator first and to see where it crosses, and then just depress it using that root. But on your quiz, now you can do that on your homework to kind of expedite the process, but on your quizzes and tests, you can't use a calculator for this chapter, or a graphing calculator. So you might want to practice using the rational root theorem. Okay, and here's a mini proof of it, where it comes from. For any polynomial that starts with a to the n, x to the n, a to the n is the leading coefficient, then a sub n minus 1, x sub n, that means you're at the next coefficient and you've lost a power. So if you start with x to the 4th, then this got to be x to the 3rd. Notice how. All the way down to the constant. If you have some factor, qx minus p, in other words, you can pull it out. We say, okay, the q's, this is a factor of a sub n. That's the leading coefficient, LC, leading coefficient. The p's are a factor of a sub 0. That's the constant. The constant. So we say the following. Take this bad boy. Since he's a factor, then when you solve him, you can set him equal to 0, or you can set it equal to 0. Solve for x. Well, qx would be equal to p. That means x would be equal to p over q. Remember the p over q that I said earlier? That's where it comes from. So, if sum p over q, remember p is a factor of the constant and q is a factor of the leading coefficient, is a root, then p of p over q, when you plug it in, is going to be 0. Where the p's are the factors of a sub n, that's the constant, we already said that. The q's are the factors of a sub n, which is the leading coefficient. The possible rational zeros are all the p's over q's. All the p's over the q's. So let's practice a couple of this. Pause the video if you need to copy the rest of that down. Okay, so I've given you a polynomial. 3x to the 4th plus 13x cubed plus 15x squared minus 4. Test the x values to see when the remainder is 0. What that means is define the p's and q's and see when you get a 0 as a remainder. Once down to a quadratic, then hopefully it factors. Once you get it down to a quadratic, hopefully it factors. Now, this guy is 3x to the 4th, which means we'd have to depress it 2 times to get it down to a quadratic. You should always check the first root again that worked. It may be a double root. Okay, so let's come up here. Let's get all our p's. Now your p's come from the constant, the factors of 4. 1, 2, and 4. The q's come from the factors of 3. Q's. Leading coefficient, 1, 2, and 3. Got to put plus or minus in front of all of them. Alright, so now we need to list all our possible rational roots, p's over q's. So take each p, 1, 2, and 4, and put it over each q, 1, 2, and 3. And this can be a little tedious, but at least, again, we're giving ourselves a shortcut. Plus or minus 1, plus or minus 2, plus or minus 4. So I've put everything over 1. Now put everything over the 2. Plus or minus 1/2. Plus or minus 2 over 2 is just 1, so I've already used that. And 4 over 2 is just 2, so I've already used that. So that's cool. Now move on to the 3. Plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Okay. I'm not going to go through the whole process in this example. I am in the next example. But in this one, I'm going to cheat. I'm going to pretend that we graphed it. And we did. And guess what? When you graphed it, it crossed at -2. Not at 1, not at -1, not at +2, but at -2. So put -2 in the hoopty. Put -2 in the hoopty. All right, coefficients. 3, 13, 15, 0, don't forget him, and -4. All right, depress it. Go. See if you can beat me. -6, 7, I'm nervous, -14, 1, -2, -2, 4, and ding, ding, ding. Did I beat you? I hope I did. Whew. Okay, so we went from x to the 4th power down to x to the 3rd power. But what did I say in this last hint? You should always check the first root that you found. Again, it might be a double root. So you need to depress this bad boy again. Put -2 in the hoopty right here. And now go from a cubic to a quadratic. 3, -6, 1, -2, -1, +2, and 0 again. Look at that. That means -2 is a double root. It does something like that in the picture. Okay? That means -2 is a double root. And now we're down to a quadratic. And hopefully this bad boy factors. But guess what? He doesn't. So you're going to have to use your best buddy, the quadratic formula. X equals -1 plus or minus the square root of 1 minus 4 times 3 times -1, all divided by 2 times 3. Answers, -1 plus or minus root 13 over 6. Those are the other two roots. Those are irrational, two irrational. And then x equals -2, that's our other root. It's one real root, but it's a double root. One real. So we got one real. I'm up in the top right corner now. One real and two real irrationals. Up here I should have put rational. 1 real rational and 2 real irrational roots. Alright, sweet. Okay, this is our last example, and we're gonna exhaust this one. We're gonna do it the hard way. Okay? Here we go. Need our p's. P's come from where? Where do the p's come from? Tell me. Do they come from the 6 or do they come from the 4? The p's come from the 4. Plus or minus 1, plus or minus 2, plus or minus 4. Okay? Where do the q's come from? The q's come from the 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, so now I need my p over q's. P over q's. So I got, alright, each p over each q. 1 over 1 is 1. 1 over 2 is 1/2. Actually, you know what? I'm going to do it the other way. I'm going to do each, not each p over each q, but each p over the first q. That's what I want to do. Each p over the first q. So everything's going over 1. So plus or minus 1, plus or minus 2, plus or minus 4. Okay, I'm done with the 1. Now go plus or minus everything over 2 now. So plus or minus 1/2. Plus or minus 2 over 2 is 1, already got it. And 4 over 2 is 2, already got it. So I'm done with him. Then I got plus or minus 1/3, plus or minus 1/6. Remember, these are possible rational zeros. At least we've narrowed down the list of infinite numbers here. All right. Plus or minus 2/3. Don't forget about him. Plus or minus 2/6 is really just 1/3. So I don't need. I've already got him. All right. So now I need plus or minus 4/3. I'm done with the 3 now. And plus or minus 4/6 is really 2/3. So I've already got him. So I'm done with the 6. Sweet. So now I begin guessing. I begin testing them. So what I do here, I'm going to show you a shortcut, a simplified synthetic version. So over here, put your x column. These are your possible zeros. Put a 1 right here in this hoopty. Up here, put your coefficients. 6, negative 11, 21, 6, and negative 4. And draw a line right here. This is your remainder column. We're going to do a couple of the steps in our heads. We've done synthetic enough to where we can do this in our heads. So here's what you do. You drop your 6, but now you take the hoopty times 6 plus negative 11. You're going to do the multiply add step together. You're not going to show your work here. 1 times 6 is 6 minus 11, negative 5. I expect that you guys can do that in your head. Now take your hoopty times a negative 5. 1 times negative 5 is negative 5 plus 21 is 16. 1 times 16 is 16 plus 6 is 22. 1 times 22 minus 4 is 18. So did that work? Did we get 0? So you know what? You can cross out this row if you'd like. You don't have to. And now you guess the next one. So now try negative 1. And we're just going to keep guessing until we find one that gives us 0 over in the right-hand column. So start back at the beginning. Drop the 6. Negative 1 and 6 is negative 6, plus negative 11 is negative 17. Negative 1 and negative 17 is 17, plus 21 is 38. If you can see that you're not going to get 0, you can just stop and go to the next one. Negative 1 and 38 is negative 38, plus 6 is negative 32. Negative 1 and negative 32 is positive 32 minus 4 is 28. But we didn't get 0, so we can cross that out. So negative 1 is not a 0. And you just keep going, guys. All right, let's try negative 1/2. All right, I wonder why Mr. Williams jumped all the way to the 1/2s. Let's try this one. Drop the 6. Half of 6 is 3, but it's negative. And negative 3 and negative 11 is negative 14. Half of 14 is 7. 7 and 21 is 28. Half of 28 is negative 14, and 6, that's negative 8. And half of 8 is 4, and 4 minus 4, uh-oh, ding, 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 0. Sweet. So negative 1/2 is our first 0. Negative 1/2 is our first zero. Sweet, I'm going to put that out here. Negative 1/2. 1 down, it's a power to the 4th power, so 3 to go. Alright, so now what should we do? We should check the negative half again, because who knows, maybe it's a double root. But now you're done with the exponents up top. Now you've got a new depressed polynomial right here. He's a cubic. This is 6x cubed. This was 6x to the 4th. Use this bad boy. Now here your remainder column is after this white line. So drop your 6. Half of 6 is 3, and negative 14 is negative 17. Half of 17 is 8.5, and 20, that's 36.5. This is not looking pretty. Half of 36.5 and negative, bleh. It's definitely not 0. I'm just going to put an X there because I know it's not 0. I'm just going to move on. So negative 1/2 is definitely not a double root. I'm going to just pick another one of my fractions. I'm going to try the 1/3 with the new depressed polynomial. And let's try him. So this guy didn't work. Cross him out so I don't get confused. Go back to this white row. Drop my 6. 1/3 of 6 is 2. Minus 14 is negative 12. 1/3 of negative 12 is negative 4. And 28, that's 24. And 1/3 of 24 is 8. 8 minus 8 is 0. Cha-ching! Sweet. So x equal 1/3 is a root. And what's even sweeter is I'm down to a quadratic. So now hopefully, I'm going to come over here to the right, hopefully this bad boy, when I set him to 0, will factor. And you know what's even cooler is you can pull out a 6 because it's set to 0. Because it's set to 0. Oh, but you know what? I noticed that this guy's not going to factor. He is certainly not going to factor. So, let's use quadratic formula. Opposite of b, plus or minus. B squared is 4, minus 4 times 1 times 4. All divided by 2. I'm going to jump straight to the answer because I think you guys can handle the quadratic formula. 1 plus or minus I root 3. Sweet. So those are my 4 roots. 2 complex and 2 real rats. Alright folks, the power of the rational root theorem always works if there's rational zeros. Very cool. Hey, hope you had hope you had as much fun as I did, and I hope you have a great night. I'll catch you later. I'm out.